Let's go back to it. Hi, yeah, my name is Sarah. I am a PhD candidate at the physics department. I study cosmic rays, which is what I wanted to talk about. I will go a bit broader than just the small scope of my own research. And actually, the field of cosmic rays is one that has always lied at the intersection of particle physics and astrophysics and space weather and geomagnetic things I don't care about and things I care about. And it started that way, and it has a very interesting history. So I really wanted to take a historical approach. So instead of just telling you what a cosmic ray is, we'll just walk down the bristly path of their discovery, because they didn't know for 150 years what they were seeing, and the magnitude of actually what it turned out to be is quite remarkable. So it's nice to look back at it that way instead of just from what we know to what they didn't know. So we'll start with the historical approach, and then I'll tell you what a cosmic ray is eventually. Then we'll just get more specific and tell you about what my PhD project is. And it's a NASA-funded balloon mission called AESOP-Lite. And I'll tell you the acronym later. It doesn't really make sense. But we flew a stratospheric balloon, and we built a particle detector, and then we flew a balloon, and I'm not going to show you data because we don't have it yet. And then I'll show you a movie though. That's going to be fun. Okay, so that's the program. All right, so the discovery of cosmic rays is one of those great scientific story where it was just a background that they were getting. It was just a signal they didn't understand for the longest time, and 150 years later, turned out it came from the cosmos. So it started in the 18th century, and the French physicist Charles Coulomb figured that his apparatus, the electroscope, was spontaneously discharging. So let me tell you what an electroscope is. So there's an engraving of it here. An electroscope is a very simple mechanism with which you have a metal bulb here, and it's connected to two golden leaves, and those golden leaves are enclosed in a bell jar. Okay, if you bring a charged rod, either negatively charged or positively charged, the charge by induction is going to travel down, and it's gonna bring those two gold leaves that were originally close together. They're gonna bring it apart, and you have a charge. Now, it's perfectly valid to assume that because it's sealed in this bell jar, that if an electroscope is charged, it will stay charged. The only way you can discharge an electroscope is by bringing a charge of the opposite sign and discharge the electroscope. So what Charles Coulomb found out in 1785 was that when he would charge his electroscope and he would go hang out and then he would come back, the electroscope was discharged. So that there must be some ion somewhere in the atmosphere discharging this electroscope. And he reported that in a paper, because they wrote papers back then too, in 1785. And for the entire 19th century, they still didn't know why. They were just, oh, it is discharge, and the electricity was the hot thing back then. And they were doing studies, and they were testing the apparatus itself. Is there a charge in the apparatus? No, there isn't. We don't know what is discharging, but it's discharging. All right, now we jump 100 years. And in the early 1900s, another French physicist, Henri Becquerel, discovered radioactivity. And that history too is a good one. It's one of those things where it's like, oh, I forgot something in the drawer and I got a Nobel Prize for it later. But he left uranium salts in a jar with some photographic plates. Because X-rays were discovered a few years before. So then everyone was interested in those rays. So then he left them in a jar, and then when he took out the photographic plate, he saw that an image was imprinted, which means that there must have been some charge emanating. And like that, they figure out that some material were radioactive and spontaneously emitting charges. Okay, that's the second step of the story. So then they went back to the problem of the electroscope, and then they figured out when they bring a radioactive source that the electroscope was discharging. It's like, okay, those particles are being emitted are discharging the electroscope. So now the question is, what's the source of this atmospheric ionization? What is the source of these charges in the air? So then there were multiple, there were multiple competing theories. One of them, since they discovered radioactivity, they discovered that some rocks were radioactive. A theory that was really favored back then was that, okay, there are some radioactive rocks that is coming from the Earth's crust, and it's coming up, and it's discharging our electroscopes. And some people were like, wait, maybe it's coming from up there. And then, to settle the question, they started bringing electroscopes everywhere. This guy, Domenico Pacini, he was this Italian physicist. He went on a boat from the Italian military, and if you want to laugh, this boat in Italian is called the Destroyer. It's like a little, so he went on this boat, and then he put his electroscope in a copper box, and then he put the copper box 3 meters down the sea, and he wanted to see, basically, what is the variation with altitude. The whole idea behind it was that they figured, if you go up with altitude and you see that your ionization is going down, knowing that the atmosphere is working as a giant absorber, basically, then you could figure the ionization must come from down, from the Earth's crust, because if we go down and it goes down, if we go up and it goes down, then it's from the Earth's crust. If on the contrary, we go up and the ionization goes up, then we can deduce that it must come from up there. That was the whole idea. So Pacini put his thing on down in the Mediterranean Sea, and then there's this. I like this one. Father Wolf. He was both a Jesuit and a physicist, and sounds like a dreadful combination to me. He was like, the Eiffel Tower. I'm gonna use it. The thing is, the Eiffel Tower was reviled back then. They was like, this ugly monstrosity. I hate it. And so the proponents of the Eiffel Tower, they're like, no, it's great, you could do scientific experiments with it. Because at the time, it was the highest building in the world. It was 300 meters up high. They were like, wow, yeah, maybe you'll figure something out. So Wolf, he was like, I'm going to study this ionization, variation with altitude. I'm going to bring my electroscope at the top of the Eiffel Tower. Those are now historical anecdotes because neither of those two experiments yielded results that were conclusive enough. Because they weren't going high enough. And so they had to go up on a balloon. And the whole thing was that in the 19th century, the early 20th century, ballooning was all the rage. And they were really, really reckless with it. And that's the part I like the most. Okay, so this is Victor Hess, and he's the one who discovered cosmic rays. Like now, if you look at Wikipedia, they'll be like, oh yeah, Victor Hess, 1912, the Vienna flight. So this is him on a balloon. Someone told me today, someone was like, I heard he sent his graduate students on the balloon, and I was like, I don't know, but that he took the picture, so I would believe that. I don't know who these kids are, but so he went on a balloon, and the whole point was that you go higher on the balloon, and then you can study this ionization. And the whole thing is crazy because first of all, the balloon was filled with hydrogen, and if you're privy to the Hindenburg disaster and other such episodes of history, it's a bad idea. If you're trying to build dirigibles with hydrogen, it's also a bad idea. So also they had no breathing apparatus, and they were going higher than any peak here. There's this guy. Then a year later, he went up to 10 kilometers up high. So they had no breathing apparatus. As you can see, they're wearing tweed. It's not very warm, and their hat doesn't cover their ears. And the thing is also, he did multiple flights at night because he wanted to see if the sun could be a source. He did a flight at night, and he did a flight during a solar eclipse. And that's scary. That's kind of scary. But Victor Hess, he got just pristine results. He was also very good with the electroscope itself. I didn't mention that, but it took a lot of improvement on the technology to get good results. But here on the left-hand side are Victor Hess's results. On the right-hand side is a next flight from this called Hertzler guy. And what you see is that clearly the ionization goes up as you go up with altitude, and that was kind of the nail in the coffin on the theory that it came from the Earth's crust. And then Victor Hess is like, it comes from the heavens above, clearly. Now, they're called cosmic rays, but it's a misnomer. A ray is usually a word that we use for light, for a photon. And at first, it was thought that these rays, this radiation, were very high energy gamma rays, because if they could penetrate all the way to the atmosphere, they had to be gamma ray. But to explain to you how it isn't, and to go on just with the rest of my talk, we must take a necessary interlude. And it's a very, it's in one sentence that an electric charge is deviated by a magnetic field. So here is the simple case that we like. So if you have a particle that is coming with a velocity vector that is perpendicular to the magnetic field vector, it will assume a helical trajectory. Now let us not burden ourselves with these terrible complex cases. But basically it just it gets really messy. But everything about this talk has to do with magnetic fields. It's all about magnets. And the Earth has its own magnetic field that, to a best approximation, could be thought of as a dipole magnet, so any bar magnet. And so you have this configuration like this. And what it means is that if you have a charged particle that is coming from the cosmos, it will have a much easier time arriving from the Earth at this latitude, at the pole, because its direction vector is parallel to the magnetic field line, than coming at it from the equator, where its velocity is perpendicular to the magnetic field line. So now, knowing that, we can carry on. In the 1920s, they put the electroscopes on boats, and then they surveyed the globe. And what they figured is that there is this latitude effect, that you have more cosmic rays, at higher latitudes than at the equator. It had to be charged particles. So in the 1920s, they finally, the community reached a consensus, and that was the birth of cosmic ray physics. But really what it was the birth of particle physics. Before 1952, when the first accelerator was built, all the basic particles that we know of from the Standard Model were discovered with cosmic rays. And the first one is the positron, and that's an important one because it's one that we study. So the positron is an anti-electron. It has all the property, it has the mass of an electron, except that its charge is positive, except for being negative. This guy, Anderson, he used this new technology. So now forget about the electroscope and think about the cloud chamber. So the cloud chamber, what it allows you to do is that it shows you the track of a charged particle. What you need to do is, there's a bug. Anyway, you just put your cloud chamber. It's gonna the charged particle is gonna ionize this condensate of water and alcohol, and it's gonna leave water droplets. And if you put a big fat magnetic field around it, what it's gonna do is that it's gonna bend the trajectory of the particle. Now and then you snag a photograph. By reconstructing the trajectory of this curvature, you can infer the charge of the particle and its energy. Now remember that, because when I will tell you what our experiment is, we use exactly the same philosophy behind it. The technology obviously has changed, but it's exactly the same idea. We're trying to find the track of a particle that we deviate with a magnetic field. So Anderson discovered the positron. That was a huge deal. And in 1936, both him and Victor Hess were awarded a joint Nobel Prize for the discovery of cosmic rays and for the discovery of positron. And the fact that they were giving this Nobel Prize at the same time is telling. And in the, so in the Nobel Prize you nominate someone. You nominate them. And And in their nomination, this famous physicist, Compton, he wrote that yes, it was late, you know, I know, Hess figured out the cosmic rays in 1912, but we were waiting to see if actually it was of any importance to physics. And then when they were like, oh wow, we were discovering all these new particles, okay, we'll give you both a Nobel Prize, that was really the beginning of experimental physics. Alright, what's next? Oh yeah, okay, now I tell you what a cosmic ray is. Okay, so this is what we know about the cosmic rays. Cosmic rays is what we call any high energy charged particle that strikes the Earth from anywhere beyond its atmosphere. Okay? The energy spectrum that I'm showing here is huge. This is 10, it goes like, what am I doing? Sorry. It has like just an enormous order of magnitude that it can reach. So just to tell you, this is the LHC, this is the most powerful particle accelerator. This is the energy that a cosmic ray can have. There is nothing more energetic that we know of. Now, on the x-axis, that is the energy, but on the y-axis is also a just beautiful breadth of, this is a flux. Okay, what a flux is it's a rate, it's a number of particles per energy, per area, per second. Basically, it's like how many you're gonna find. It's a count. Just think of it as a rate. But here you have a high rate. But let me tell you here about the slow rate. This slow rate, if I translate it to word, means that if you want to detect these highest energies, you have to build a detector that is 1 kilometer square, and you have to wait a century, and you will detect one particle. So it's very tricky, but to detect these particles is to probe new physics, is to probe beyond standard model, is to probe things that you cannot probe with the LHC. Now I've talked about the high energy, but really what we study is here, and it's not even on this axis because it's so low energy that it's not even that, but whatever. But the thing is, the detection method that you choose completely depends on where you stand on this y-axis. So what is your flux? So because we're here and our flux is pretty high, we can use a balloon. But I'll get to the balloon later. We'll talk about balloons. About cosmic rays. We think the mystery of their origin is still kind of unknown, but we think that they come from the explosion of stars, supernovae explosion. You need something extremely energetic to accelerate particles to those energies. About the majority of them, like 90% of them are protons, and only 1% of them are electrons. This electron, this 1% is also what we study. So we're like marginal. We're way marginal. Okay, back to the magnetic field. So cosmic rays, they come from somewhere. Then they travel through space. Then they travel through the galactic magnetic field. The galactic magnetic field will scatter them, it will isotropize them. Okay, say they survive. They reach the boundary of a heliosphere. And I'll tell you about the heliosphere. The heliosphere also has a magnetic field. Then they come. And if they are at a low energy, what we call low energy being like 10 GeV, which is a unit of energy, they will also get completely scattered by this magnetic field. Say they survive. They come to the magnetosphere, the Earth's magnetic field. Say they survive. Then they reach our detector, and they come through our magnetic field, and then we detect them. So it's all about magnets. But this is the question that we're interested in, is what happens when those cosmic rays that are low energy, when those cosmic ray electrons travel through the heliosphere? How are they modulated? Because they're heavily modulated, but we don't know everything about it. Right, I put this slide there. This is what happens when they reach the atmosphere. This is a high energy particle, and it reaches the atmosphere, and the atmosphere has 80% nitrogen, 20% oxygen. It has all these nuclei. So it comes and it scatters, and what it creates is this cosmic ray showers. We call this a cosmic ray shower. But we're interested in them before they scatter. This whole thing is what they were detecting in their electroscopes, is those secondary particles. This whole thing is our background. It's a problem. Okay, our heliosphere. So I've told you that, you know, if they make it, they reach the boundary of our heliosphere, but what is the heliosphere? So the sun has a hot plasma around its corona, right? And it's so hot that it's no longer gravitationally bound. And it's expanding. But it doesn't expand in any sort of symmetrical way. It assumes this shape, and then, you know, you see that, like, that sunny dot, that's the sun. And what you see is that it expands way beyond the realm of our solar system. And it stops at the boundary of the interstellar medium when the pressure of the heliosphere equals the pressure of the interstellar medium. So it's about 100 astronomical units. 1 astronomical unit is the distance between the Earth and the Sun. Now in 1977, NASA sent 2 probes, Voyager 1 and Voyager 2, and amazingly enough, they still function. And amazingly enough, they have crossed the boundary of our heliosphere. And they detect electrons. So they detect the cosmic rays before they get scattered of the magnetic field. Okay, that's important. The fact that those 2 probes are there, it matters to our experiments. Okay, so the sun has a cycle. There's a solar activity cycle. You might have heard of that. You were like, oh yeah, the sun is there are a lot of hotspots in the sun right now. It has to do with the solar activity cycle. So there's a very well measured 11-year cycle that the sun has, during which it goes from a solar minimum, very smooth surface, no hotspot. When the sun's surface is smooth, the magnetic field is nice. It's not turbulent. It's not like those panels that I didn't want to talk about. Then during those 11 years, it comes at a maximum solar activity, very turbulent. The tilt of the magnetic field grows. It becomes more messy. And then at the end of the 11 years, it comes back to minimum. And what has been observed from very early on is that there is a very clear anti-correlation between the solar activity, which is here in orange, and the count of cosmic rays that we get on Earth. Because particles get scattered by magnetic field, when the sun is at a maximum and the magnetic field is at its most turbulent, it's going to be very good at scattering those particles and not allowing them getting to us on Earth. So this phenomenon, like how the cosmic ray signal on Earth is very dependent on the solar activity, is what we call solar modulation. And that is what we study. We study the solar modulation of cosmic rays. Ah, Roger. This is Roger. Okay, now I tell you about AESOP-Lite. I tell you about our balloon mission and what it is we're interested in. So we're interested in the solar modulation of cosmic rays, I've told you, but not only cosmic rays, of electrons and positrons. Okay? And those are our goals. This is what we're trying to answer. Well, the first one, I guess, is not a question, but we want to be able to compare the signal of electron here on Earth, where the cosmic ray has been modulated, with those of Voyager that gets us the non-modulated one. And the reason for that also is that Voyager here, those are the black dots on this plot. So on this plot, you have the energy on the x-axis, and again you have a flux. So just a count. You can think of it as a count on the y-axis. So this is the unmodulated spectrum. And the thing is, there isn't really a mission that has overlapping energy range as Voyager. So this is why we're like, oh, we're gonna build something. Then the second question, and then we get a bit more into the detail of what we do, is that we want to understand why this electron spectrum, so these points are from previous measurements, why this electron spectrum suddenly turns up. All the explanation for them are completely ad hoc. They're like, oh, okay, we tweak the coefficient, the diffusion coefficient, and then boom, it goes up. But it's not very satisfactory an explanation. It's not very physical either. So the way for us to understand what's going on is to be able to distinguish electrons from positrons, because a lot of those these measurement points that were made by our collaborators on a previous balloon mission, they had an instrument that couldn't distinguish positron and electron. So when you're able to distinguish matter and antimatter, that really points to the origin of where they're coming from, or it just gives you a lot more information on it. And so this is why we want to know what the positron, what we call abundance, is below 200 MeV. We want to know how much positron there is. So this is what we're trying to do. And to do that, we built a. Oh no, I guess that's not done. Okay, this is our team. This is our team. It's a very small team. It's only 2 universities. It's a team at the University of Delaware where they're expert of cosmic ray studies. And John Clem, our PI, is the one horsing around in this GIF picture. And this was taken in Palestine, Texas, where NASA has its scientific balloon facility. And then it's just my advisor, Professor Robert Johnson, and myself on this team. So it's a family affair somewhat. And then there's Roger, that you'll see more of. He's our mascot. He's here. Okay. So what is our instrument? Our instrument is quite simple. In light of what I've told you, the basis of it is the magnet spectrometer. A magnet spectrometer, basically, it's a big magnet, and then it's a tracking. It's 7 layers of what we call silicon strip detector. This is a tracking device. Just in the same way, in 32, when Anderson could take a picture of the track of the particle, this is what we're trying to do. But we're not taking a picture. We're just having, the strip tell us the position of the tracks. And the reason why we put a magnet is we want to deflect the trajectory of the particle. And if the trajectory is deflected and we can trace it back, then we can reconstruct the energy of this particle. So that's like the basis of it, is a magnet spectrometer. I did bring a gimmick. I don't know how helpful it is, but this is a particle going through a magnetic field. It's a gimmick, it doesn't do much. Anyway. But yeah, so you imagine like a particle going through, and before we detect it, it has to go through this entry telescope that we call. So this is made of 2 scintillators. The principle of a scintillator is that if you have a charged particle, excuse me, above a certain energy, it's gonna scintillate a photon that then is gonna be detected in a cascade. So basically, it tells you there is an event coming. This part, this conical part is called a gas Cherenkov detector, and it's an important thing. The principle of a gas Cherenkov detector is that you set a gas at a certain pressure, and the gas is going to scintillate a photon only for a given mass and energy of a particle. The idea is that it's the optical equivalent of a sonic boom. The idea is that there is a medium in which the I'm gonna get it wrong. I'm gonna get it wrong right now. Let me skip that part. Just got confused all of a sudden. But the idea is that this is gonna discriminate for particle types. Remember I told you there's like 90% of cosmic rays are protons? We don't want these 90%. If we were to be triggering for all this 90%, we will just, our signal to noise will be terrible. So we put this so that we don't have to trigger on the 90%, because this is not going to scintillate if a proton below certain energy is going to come. It's only going to scintillate for an electron. So it's an important part of a detector. So that's the schematic, and that's the picture. And we cut someone's hand so that you can know how big it is. And it's not very big. The whole thing is maybe that big. Doesn't mean it cannot be grand, though. So really not that impressive, but this is how it is on a lap stand. Then I put a picture of the magnet. It has a certain magnetic field magnitude of this. Speaks to you 0.35 Tesla, not very important, but enough. Basically, the magnetic field strength is gonna give you the range of your energy range. It's gonna be like, okay, a particle of that energy is gonna be deviated, and a particle above it is just gonna look like a straight track. So the magnetic field strength does that. And this is the tracking board, that's the tracker board, that's what my advisor and we developed here in Santa Cruz. If you don't believe me, there's a redwood tree here. And we have 7 of these, and these are, those are the silicon strip detector. They're really widely used in astrophysics and particle physics. They're currently on a NASA satellite called Fermi that was also partly developed here. And then they're connected to all these electronic ASIC front-end chips and all of that. But basically, the idea is that this is divided in 768 strip that are, you know, about they're 60, so the resolution that we can get is 66 micron. A hair is about 66 micron. So that's the resolution that we can get. So that gives us a coordinate, you know, it will tell us which strip it has hit, and then we know where in the detector it is. So it gives us 2 coordinates because we know where we place it, and then we know where it hits. And that's our instrument. And this is how it looks in the event display that we've developed, because then you have 2 views. You have 7 detectors, and you put 3 of this detector in one of the view where the helix will just look like a straight line. And then you put 4 of these detectors in the bending view where you can reconstruct that curvature, and that curvature tells you the energy. And this is what the 2 views look like. For an electron, it bends one way, and for a positron, it bends the other way. That's the whole principle of it, basically. And then, you know, we have 4 points, and we fit a parabola, and the radius of curvature of this parabola will give us the energy of the incoming particle. So it's not that, like the whole principle of it is very standard in particle physics. All right, so the project timeline. So in 2015, 2017, we developed these boards. And then we tested them, and you know, there's ionization everywhere, so you just leave them in the lab and you wait for muon to hit you, and you have cosmic rays for free, and you calibrate your detector that way. So that's what I was up to the first year or so of my PhD. And then we we went to beautiful Newark, Delaware, and you should go there. And then we assembled the detector within the greater instruments, you know. So then they had like all the other parts. They're like, okay, we're here, and then we like assembled it, and we tested it for about a year. Then in the winter 2018, we went to Palestine, Texas. Also, you should go there. It's great. Where NASA has their balloon facility, and we were there for about 2 months. And what you do there is that, well, you test your instrument, you test everything about your instrument, and then you get flight ready. You pretend like you're gonna fly, and then you don't fly. So that means that you put it in the gondola, and I have a picture of that. You put it in the gondola, you communicate with it. NASA puts all their communication antennas. You send command. You make sure that all the what we call uplink and downlink, like sending a command and receiving a command, works. And then you just, you know, test for temperature, pressure. You put it in like near space condition to make sure that your detector is not gonna like explode in the middle of the flight, because that has happened, and you know, you don't want that to happen to you. Okay, then when everything is ready, you pack everything up and you put it in a sea container, and then you put it on a ship, and it goes from the port of Houston to Sweden. Now we go to Sweden because we need to be near the pole. Remember the Earth's magnetic field? We need to be where what we call the geomagnetic cutoff is low. That cutoff is the energy, is the minimum energy a cosmic ray particle should have for it to enter the Earth. So we need to be either in Sweden or in Antarctica, is where we can fly our balloon. So we go to Sweden in the spring, and we spend another month and a half. And then we fly the balloon. Then we launch it. It was beautiful. It was our 3rd launch attempt when we did. And honestly, thank God we launched it when we did, because I was getting tired of the whole thing. I was like, okay, it's a lot of hurry up and wait. Because like just the scrap, just like when they're like, no, just kidding, you're not gonna fly, that takes like 7 hours. Oh, I got time. But so then we flew for 5 days. And I'll show you a little clip of that. We flew for 5 days, and we landed in Ellesmere Island, Canada. So when you fly from Sweden, you cannot have a full circumpolar flight, which you would have in Antarctica. Because if you do that, once you reach Canada, you get to Russia. And that's not allowed to fly over Russia. So you have to terminate the flight. So I'll tell you about that later. You terminate the flight and then you get your instrument back. And then since then we've been working on the data analysis, but Roger has just been just in immense tomfoolery since then, you know, he's not very concerned by the whole thing. Alright, so now on the business of balloons. So you may recall the tragic 1997 Thanksgiving Macy's Days Parade Barney incident. And this just goes to show what can happen when you try to fly large, unwieldy structures. It can be very funny like that. Okay, if you go back home and then you type on YouTube NASA Balloon Australia, go watch that. I didn't want to show it because they don't like it when you remind them what happened. Alright, but the balloons are big, but it's impressive. It's impressive. So we flew on a 40 million cubic feet balloon, and that's a small one. That's a small one they have. But just to tell you, first of all, the balloon is made of like this super thin film that basically has it's like a sandwich wrap. It's just like a giant sandwich wrap. I mean, I'm sure there's more science that goes into it, but that's all I know. And then you fill with helium, but you don't fill it completely, because, you know, a gas expands in the volume that is given. So you don't fill it completely before you launch it. You fill it just a bit, and then it goes up, and it takes about 3 hours to reach float altitude. Our float altitude is about 38 kilometers, 140,000 feet. Yeah, so 2 hours to reach float altitude, and then once it reaches float altitude, it has a volume of 195 Codier blip. So when I read that the first time, I was like, whatever. I don't know what a Codier blip is. Should I be impressed? Then I looked it up. It's big. 200 of them. Should be very impressed. So to go back to that thing, well, I guess we're gonna have to come back to that then. Okay, but also the balloon, it's attached to this. Well, I forget how it's called, but it's attached to something. And then here it's attached to a parachute. And when you're ready to terminate your flight, so when you reach a remote part of Canada, you terminate your flight, you send a command, and this thing explodes, and it detaches the gondola where your instrument is from the balloon, and then you hope the parachute works. It works for us, but sometimes it doesn't work. You hope the parachute works, and then they go and they retrieve it, and then your instrument is like working and alive. It's really quite incredible. Alright, so okay, the joke. The balloon mission. The balloon mission. Okay, so this is what the fully integrated instrument looks like. So it sits in this pressure vessel here because we need it to be at atmospheric pressure. So you do a whole bunch of tests to make sure that this doesn't leak and that the temperatures are right inside of it. And then all this gondola, you have all your black box storage, you have your battery box and other sort of things. On the other side, you have all the communication boxes that NASA adds. And then they put many redundant channels of communication. So you can send commands, you can receive command, you can receive data. Like, you know, you're monitoring the whole, like, we did not sleep for 5 days. Because you have to make sure that your instrument is working. And then all the power is supplied by the solar panel, and here at the bottom is the ballast. And they put a lot of ballast. And the ballast is necessary because you reach float altitude and then you're just floating on these stratospheric westerly winds. And the thing is, the balloon goes like through diurnal altitude variation, because when the sun is out, it's nice, we're like a high altitude, but when the sun is no longer in the horizon, the gas cools down and it contracts. it cannot lift as much, and the altitude of the balloon drops. For us, it matters very much that we're at high altitude, because the atmosphere is basically our background. You remember that image of the cosmic ray arriving in the atmosphere and then having all this shower. All this shower, it gives us all these secondary electron and positrons that we're not interested in having. I mean, we have them, but this is a background for us to subtract later, basically. So this is the final test that that NASA makes you go through. This is called the hang test, or compatibility test, and then hang it from a crane, and then you, from the computer, you send all the commands and you make sure that all communication works and that everything works, and then they're like, you're ready to fly. And then you fly. So we started from Sweden, and then, you know, I told you about the diurnal variation, and you go up and you go down and you go up and you go down. And I will point out that this tells you what this geomagnetic cutoff is and how it varies, because it also varies between night and day, and I won't go into too much detail, but there is a magnetosphere, and the Earth is rotating around this magnetosphere, and where we are in relation to this magnetosphere changes what the cutoff is. But really, for us, our data analysis, really our data starts here, where the cutoff is essentially 0. And this is kind of just like, oh, well, too bad, you know. But if you fly from Antarctica, you're at 0 cutoff the whole time, so it has a lot of advantages. And then you land in a giant ice sheet in Canada. And I did not go on recovery, but our engineer James did, and he's a pilot, so he was very excited to fly on this Twin Otter. And then they were looking for it, for the balloon, and he promised me he would look for Roger first. And then he sent me this picture, and I was like, yes, worked. NASA gives you these. I don't know if there's a picture of it, but they give you these crash pads that are basically like this little Amazon carton box, essentially what it is, and then you see it and you're like, do you think this is going to support 1,000 kilograms? I don't think so. And so then usually they just crash on the solar panels and you have to buy new ones. So we got the instrument back, they shipped it again by plane, it's at the University of Delaware, it's working again. We got funded for another flight, hopefully from Antarctica, so that will happen in some years where I no longer will be here. And so, I guess that was like my final real slide. I will say something about the data analysis, because it must include some science. So it's still ongoing because basically the heart of it is getting that is subtracting this secondary particles that come from the interaction, the interaction of the primary cosmic ray with the atmosphere. And so to do that, you basically simulate your entire atmosphere, and you simulate all the particles, all the cosmic ray spectrum, and then you see what the contribution is. So it's computationally super heavy, and it's not a trivial task. But at some point we'll get some results. Okay, I want to show you a movie. But I will, and that will be the end of my talk. When I knew I was going to work on a balloon experiment, I was very excited, and I worked on a balloon experiment in my undergraduate too, and I was like, finally I'll fly something. And I was like, well, I must fly someone, so I wanted to fly Roger. And I was like, we have to put a camera on the balloon, because why not? You know, we can, so we will. So we did, and it worked out great, and we took a time lapse. We took a time lapse of the ascent, and then really what I like to do is write music and play music, and I have a band, and we're called Salmon Hammock, and they're somewhere in the back. So we thought we would write a song, would make a song and record it and set it to a movie, because it's nice. So we did, and I'll show you the whole thing right now. And it's quite bombastic, you know, but it's okay.
Close your eyes.
Is it loud enough?
Sunrise is 2:31 a.m. Good copy, sir, good copy. Roger, is secure on board. Sunrise is 2:31 a.m. Good copy, sir, good copy. Roger, is secure on board. The stratosphere. Final boundary strongly. Break away.
Roger, do you hear me? Are you there? Yeah, is it scary? I know you think I've left you for dry. Don't forget me, koalas don't cry. If the world does end falling on our heads, you'll be the first one saved. Keeping a data straight, a detector in place, counting the cosmic rays. Welcome to the world of line of sight and satellite. Did you get the bite I sent you? 5B31, send me one too. Roger, you see the world from above. Are you wiser for it? My friend, tell me why electron flux is so high. How could life itself ever compare? 132 hours of madness, 40 kilometers, zero disaster. That much closer to the stars. To you